Okay, this is the alternative to practical section. You're given an equation and a lot of information about the experiment, and it asks you to state the unit of C. Well, to state the unit of C, we need to know the units of everything else. So we rearrange the equation. C equals T d root G. T is in seconds, D is in meters, and G is in meters per second squared. So meters per second to the minus 2. We're taking those out of the square roots. The square root is the power of a half, so that's seconds, meters, meters to the half, seconds to the minus 1. And the seconds cancel, which gives us a unit of meters to the 3/2. Student records the time for 20 oscillations. How does this lead to a more accurate measurement of the time for one oscillation? Well, first of all, your absolute uncertainty is going to be the same. Whoops. So that means the percentage uncertainty is going to be much smaller because the value that you're measuring is bigger. So the percentage uncertainty is smaller. So that's one reason. The other reason is that we're taking an average here if we measure 20, which reduces random error. Okay, part C. The first thing you have to do is just draw a line of best fit. I don't have a ruler at the moment, so I'm just going to do it freehand, but I think, yeah, the iPad will sort it out for me. So line something like that, goes through or very close to all of the points. Suggest whether these data are consistent with the theoretical prediction. Well, the theoretical prediction from the other page was T equals C over D root G. Which is saying that if C is a constant and G is gravity, so that's a constant, then T is proportional to 1 over D. That is supported by this graph because it's saying that T is directly proportional to 1 over D, which is shown by the graph because it is a straight line through the origin. Remember, if it wasn't through the origin, then it would not be because you'd have a constant here. So remember to always state that it's going through the origin if it is. Okay, final part. The numerical constant is 1.67. Determine G. Well, we go back to our equation again, which is T equals C over D root G. We want to rearrange that, obviously, to find G, which gives us... before we do that, actually, sorry, we want to determine the gradient of the graph because we've just decided that the equation of the graph is T equals 1 over D C over G. This is our y-axis. That's our x-axis. And that's our gradient. So the gradient is C over G. So gradient, C over root G, sorry. So the gradient is C over root G. We need to rearrange that to find G. So G is C over the gradient all squared. We've got C from the question, but we need to find the gradient. If we go back to the graph, we can find the gradient here. This dot, remember, the larger the triangle you use for the gradient, the better. So I'm going to use this dot here, this top dot, and that's about 5, maybe 5 in a little bit. And here it's 2.5. So the change in y over the change in x is 2.7 divided, because it's going from 0, so that's the change in y. To, let's just say 5. So 2.7 divided by 5 is the gradient. So the gradient is 2.7 divided by 5, which is 0.54. So G equals 1.67 from the question up here, divided by 0.54 all squared, which gives you an answer of 9.56. of second squared. Now you're given a range by the mark scheme. The mark scheme says somewhere between 8.6 and 10.7. So any of those are right.